Force. We can feel it everywhere, causing motion or changing state of motion of moving objects. What is a force? Before getting into the definition of force, let us try to understand it. What do you see in the picture? A tissue box and a pot resting on a table. Now, let us apply a force on the tissue box. Yes, it moves. The force results in motion of the body. What happens when we apply the same force on the bigger pot? The pot remains at rest even though the force is trying to move it. Now, let us increase the magnitude of the force. Yes, it moves. So, force is an effort that produces or tends to produce motion. The reverse is also true. A force stops or tends to stop motion of an object. The bigger force applied on the pot resulted in sliding of the pot. Let us put a small stopper on the table. Now, the pot doesn't slide even after application of a bigger force. What if the same force is applied at the top edge of the pot? Oops, it toppled. From this, it is clear that the effect of force depends on its point of application as well. Why is it resulting in a different behavior? We will discuss that as we progress further. We can summarize that force is characterized by magnitude, direction, and point of application. From the tipping action of the pot, it is clear that force may create a turning effect as well. Turning capacity of the force is called moment and is quantified as the product of force and the lever arm. Lever arm is the perpendicular distance of the point under consideration, which is called moment center, from the line of action of the force. So, we have seen that the application of force is causing either continued equilibrium or translation or rotation of bodies. Before analyzing the causes, let us try to get a brief understanding on different systems of forces and their resultants. Multiple forces acting on a body can be considered as a system of forces. Let us quickly review some of them. Consider a body which is acted upon by a set of forces. It can be seen that the line of action of all the forces are the same. Such a force system is called collinear forces. Orientation of forces can be in both the directions. Consider a simple collinear system where two forces of equal magnitude and direction are acting on the body. As the direction and line of action of both the forces are the same, a net force of 2F will be acting on the body and result in translatory motion of the body along the line of action of the force. Do a set of forces always result in motion of the body? Consider another scenario where one of the forces is opposite in direction. As the forces are equal in magnitude, the net force will be 0 and the body will be in equilibrium. In case one of the forces is larger in magnitude, a net force will be acting along that direction. The body will have translatory motion in the direction of the net force. So, a set of collinear forces can result in motion due to net resultant force or state of rest due to equilibrium of forces. Consider another system where forces are oriented towards different directions. However, the line of action of the forces pass through a single point. Such a system of forces is called concurrent forces. A view from a different angle reveals that all the forces are in the same plane, and so this can be considered as coplanar concurrent forces. Additional forces oriented along different planes make the system non-coplanar concurrent forces. Consider a simple concurrent force system with two forces F1 and F2 acting at an angle theta. do an algebraic sum represent the net resultant force? No. However, these two forces can be combined to get a single resultant force. The resultant will have the same effect on the body as compared to the combined effect of two individual forces. The process of deriving the resultant force is called composition of forces. The fundamental law of composition is parallelogram law of forces, which states if two forces acting simultaneously on a body are represented in magnitude and direction by two adjacent sides of a parallelogram, then their resultant can be represented in magnitude and direction by the diagonal of the parallelogram passing through the point of intersection. Further details on composition of forces are covered in a separate video. Suggest watching the same for clarity. The body will have a translatory motion along the line of action of the resultant force. Now, assume that a force equal in magnitude but opposite in direction is also acting on the body. This is equivalent to three concurrent forces like this. The third force will set the body in equilibrium and is called equilibrant. In some other system of forces, all the forces will not be passing through a single point. Such system of forces is called non-concurrent forces. Two equal parallel forces in opposite direction or a set of parallel forces in same direction are special cases of non-concurrent system of forces. Two parallel forces acting in same direction will have a resultant equal to twice the magnitude of the force and will be acting at the middle location between the two forces. The body will have translatory motion along the line of action of the resultant. Now, consider both the forces are acting in opposite directions. In contrast to earlier cases, these opposing forces of equal magnitude will not result in equilibrium of the object. As the net force is zero, no translatory effect is generated by the system of forces. However, it will have a rotational effect on the body. These equal parallel forces in opposite direction are called coupled, and further details are covered in a separate video. In order to make the system in equilibrium, another couple having same magnitude but opposite in direction must be acting on the system. Now we have briefly touched upon force, moment and how combinations of the same are causing resultant motion or equilibrium of bodies. Detailed review of composition of forces and equilibrium of bodies are covered in separate videos. With this knowledge, let us review different responses of the ceramic pot as seen in the beginning. Case 1. Continued equilibrium with application of horizontal load. This indicates the presence of an equal and opposite force acting on the system. Where is it coming from? Being the only contact with external bodies, this force must be developing at the bottom surface. This opposing force developed at the contact location is called friction. Details are covered in separate videos. Case 2. Object move forward with higher applied horizontal load. The frictional resistance offered by the contact location has got an upper limit. When the magnitude of the applied load exceeds the limiting value of friction at the contact location, motion is initiated. Case 3. The force equilibrium is maintained with the stopper. The stopper offers increased horizontal reaction as per the applied loads and equilibrium is maintained. Case 4. Tipping of the pot with load application at the top of the pot. Consider a gradual increase in applied horizontal load. It can be seen that the object continued to be in equilibrium for a while and then tipping is happening about the stopper. It is obvious that applied horizontal loading is causing rotational effect on the body. For the body to be in equilibrium, there must be an opposing rotational effect acting on the body. Where is it coming from? Yes, self-weight of the pot is generating restoring moment and is trying to establish equilibrium. The overturning moment generated by the applied horizontal load continue to increase as per the applied load. However, the restoring moment has got an upper limit and the same will be equal to self-weight times the distance to the tipping point from the line of action of the self-weight. This will be experienced just before tipping, and at that particular moment, the entire self-weight of the pot will be acting at the tipping point. Equilibrium is lost with further increase in the applied horizontal load and result in tipping. Detailed explanations are provided in separate videos. Suggest watching them for clarity.